So any topic which you want, which should be discussed in detail? Yes, come on. Till backpropagation, like then this thing we'll discuss in detail, and decision tree also because it's an important topic, I can't leave it as it is. Though we don't have that much time also, so I'll come up with the numerical example and I'll give you all the brief overview of the things which are like formulas and all and everything, like what is the specific things, like brief introductory lecture I'll give about this decision tree, and then we'll switch to MCQs. Any other topic which you are facing difficulty and you don't want that it should be only MCQs and it should be detailed lecture, you can tell me. Though with MCQs also, I'll try that we'll be I'll explain in detail about each thing. And one more thing, uh, there is an extra class. Like this is week 10th now. Okay. So only 2 week, this class and other 2 classes are left for me, and one extra class I can take. So I'm thinking to take for 2 hours. So can you suggest me, or which day you are comfortable with, except Sunday, because Sunday I'm not free, from 5th October to 16th October. Or maybe we'll discuss at the end of the lecture. You can tell me, or you can write in the chat which day or which date is comfortable for you guys. I can also, I'll teach on that specific day. And 12th. Okay. What about others? What is 12th of October? Which day? Sunday I can't. Sunday it's not possible for me. Any other day except Sunday. 13th, 11th. Okay. Yes, Saturday, same time. Okay. Okay. Mostly people are saying Saturday. And what about others? So it's fine for me. Saturday I'll teach 11th. Okay. 4 or 11th. Okay. Okay. So I'll see 4th. 4th I can't take. They are telling me only to take from 5th to 16th. So I think 11th is the Saturday, which I'll take. 4th, there is no slot for 4th. So Saturday I'll take. It's fine. Okay, let's start. Ma'am, if possible, can you take sessions after 7 p.m. because we are having problem with college timings. Okay. 7 to 9. Okay, I'll check with the team if it's allowed. Because this was the last, like 6 to 8 is the last slot. If I'll ask for 7 to 9 lecture on Saturday, if it's possible. But Tuesday lecture will be 6 to 8. I can't change this slot. It's not allowed. But the Saturday one, I'll ask. Let's let's not waste time and start. So my screen is visible. Any doubt in the last class? You guys are clear with the the way we had done some MCQs, the ANN part. So can someone give me the brief intro, whatever we have, a brief summary, whatever we have done in the last class, so that it should be easier for the others also, and I should also get that you are getting the things. We have solved the MCQs as well.
Ma'am, we were talking about artificial neural networks. We were talking about the very first one, which
MacLupit.
was some, yeah, and then we were talking about perceptron.
And then we came up with this 3-layer architecture.
Yes,
And
yes.
this is basically the input. These are the weights. This is basically the hidden layer, and this is the output layer. This is a standard 3-layer architecture which we were talking about, and then we came up with the perceptron. And I hope so. You remember that that we did that there should be a non-linear function And though I answered that step function is basically not like can any one of you tell me that why non-linear function was needed here? Why not linear?
Because if we took linear functions, then it would be as good as using one linear function.
So it will be as good as two layers only. Why to have three layers? It's just stacking up of three layers. That makes no sense here. So why we need non-linear function? Because we have to solve the like the functions like XOR and all, which can't be solved by linear functions. So that's why. And why we took sigmoid specifically? Can someone answer now? Sigmoid, tan function. Why we are using these type of functions? Any specific reason for using sigmoid or tan? Come on. Come on, come on. I hope you guys know.
Sigmoid is for 0 to 1 values. It'll anything below zero point 0.5 will go to 0, and anything above zero point 0.5 will go to 1. And tan H is same from -1 to 1.
That is fine. That is the difference between sigmoid and tan. Now I'm asking why only sigmoid? Like earlier, in earlier case, we were using step function, if you remember. So what was the drawback in the step function which was overcome by the function like sigmoid or tan? Yes, come on.
No, ma'am, I don't remember this
Uh-huh.
exactly.
Someone has answered correctly. Vimlesh, yes, you are correct. Step function, they are non-differentiable. Remember, Gaurav, now that we discussed that they're non-differentiable in
Yes, yes,
sigmoid.
yes,
Now, so now sigmoid, it's non-linear as well, and a non-linear function which is differentiable as well. So step function in perceptron that was non-differentiable. So that's why we have chosen here sigmoid or tangent. So then we discussed about this three-layer architecture, and then we discussed one more thing that why not more layers? Why only why we stop at two layers? Like these more layers, will it add some like we go to DNN, that is deep neural network, though we are not discussing in this course. But why the people add more layers? Obviously, we discussed in detail that if I have more like two layers, then we I have to have more. If the problem is complex, there should be more neurons. So that's why if I want to have fewer neurons, then I can switch to more layers. And in practice, I can also use this like reuse the features as well, and it is more efficient as well. But I should have a trade-off between more how many layers I have to take. That is basically when we'll implement empirically, we'll see that how many layers are needed and how many neurons are needed. Then we saw that okay, there is we can solve through like we have done a regression loss function as well as the classification as well. This classification cross entropy loss we have done in this logistic regression also. Again, I'll tell you, please revise this logistic regression lecture in which we have discussed this cross entropy loss function, how we have written this, we have actually solved in detail. And this is regression, which is a regression means numerical, which is simple only target minus whatever we have this for output function is. So the MSC basically. Then we did some MCQs for that. Now coming to the next part where we left. I think here differentiation only we left here. So now basically this is now backpropagation we are going to study in this three-layer architecture. How do backpropagation work? So maybe let me draw this diagram here so that I shouldn't go back and forth. This three-layer architecture, or you'll remember this is X, alpha, Z. So basically it's like X are the input here. Though I'm not drawing in detail, these are the alpha, the weights, and these Z are basically the hidden layer, These beta are the weights here from hidden layer to the output layer, and this is y. Fine, I'm not drawing in detail, just I'm giving you this information so that I shouldn't go back and forth, and you should know what is this. So what is Z here? The hidden layer. Now, one more thing. We discussed here that this function basically, this function which will, this is basically the sigmoid function. That is what we did. And this can be a sigmoid, like this can be either linear function or non-linear function. Like we have discussed now, in which case it should be linear, in which case non-linear. I think there was a MCQ also. Regression and classification, I'll not go there. So now what we are doing here is, I have to see maybe M and K. Wait a second. This is P, this is M, and this is K. Any doubt till now? Then only I'll switch. I'll go forward because it's a very important topic. Back propagation. Any doubt till now? Who were in the last class? Please, can you give me thumbs up? Are you getting? You got everything? I have just revised now also. Only one thumbs up. Yes, Yashwant. Sachin, I think you were also there. More, yes, Vimlesh, more neurons required for extracting more features. More neurons required for extracting, yes, absolutely. So, till now, I hope so. Whosoever was in the last class or whosoever was not also, I think so. I have discussed it so that how come a deep network mitigates the need for having more neurons? Can someone answer? How come a deep network mitigates the need for having more neurons? See, Vimlesh, what I'm saying is here we have 3-layer architecture, which means that I'm having 3 layers. Now, if I have more layers, which means the deep network, then, Gaurav, if I have more layers, which means I have suppose 5 to 10 layers, which means then I'll not need, I have a complex problem. If I'm solving through 3-layer only, I have to solve because what do deep neural network do? As you are only saying that we are basically extracting the features from them. And if I have only 3 layers, in each layer I am extracting some features. Okay, this is basically if I'm writing or like this is handwritten object or these are clothes also. Some features should be extracted in each layer. If the number of layers are very less, then obviously I need more neurons to extract the features. And if the number of layers are low, very 5 to 10 layers, then lesser neurons will be needed to extract the features. Because if the second layer is doing some work, then the third layer will do some work, then fourth layer will do some work. So that's why relatively lesser neurons will be needed. Is it clear, Bimlesh? Should we proceed? Deep network helps in having less compute. Okay. Can someone answer deep network helps in having less compute power or no? Come on. I want you guys should answer. Is the answer true or false? So someone is answering no, more power needed. Someone is saying okay. What about others? What do you think? Yashwant, Sneh, okay, Sachin has answered. Gaurav, Gautami, yes. What do you think? Bimlesh? Okay, Bimlesh has only asked. Yes, what about others? What do you think? Actually, yes, more power is needed. Now you'll ask me lesser neurons, more power. Why more power is needed? Come on. It sounds like a paradox. Like I am saying in one way that okay, uh, like what I'm saying. Okay, let me write here so that the confusion shouldn't be there. So one very nice question, Bimlesh, so that others' doubts should also be like solved here. So one way I'm saying, like if I have a shallow network, which means that I have only 1 2 layers, then it may require exponentially large number of neurons. On the other hand, if I use deep neural network, I'll require far fewer neurons than the shallow network. So if my shallow network, it is it needs I'll say 1,000, it may need 100 here. But what I'm saying is the other question is like as you have asked, it's like computationally expensive. Okay, Bimlesh, if no, then shallow network with more neurons is as good as uh, deep neurons with less neurons. Wait a second. If no, then shallow network. Okay, this shallow network with more neurons. Okay, is as good as deep network. Actually deep neural network with less neurons, or isn't it? Okay. Now he's asking. Okay, one way we are saying this. The other part, what we are saying is that deep neural network, because of the more layers, it becomes, though it has lesser neurons, but it is computationally expensive. That is what we are saying here. Now your question is, if no, then shallow network with more neurons. Okay, shallow network with more neurons is as good as deep network with less neurons. Now can you okay? Now he's asking that whether it is as good as that, or like shallow network with enough. Okay. Now suppose I in the shallow network, the problem suppose is it's not that complex. The problem is not that complex. I don't need that much of neurons. So shallow network with enough neuron is as good as the deep one. Then I can say. But if the problem is complex, I do need feature reusability. Though I'm not going in detail because we are not here like learning about deep neural network. Their features reusability is there, and that's why we use their we switch to deep neural networks. Though it's sometimes computationally expensive, but we should have a trade-off, like how many layers should be added, so that the problem should be solved, and at the other time it shouldn't be that much computationally expensive. But if the problem is not that complex, then as you said, that shallow network with more neurons with with the enough neurons is as good as the deep network. Vimlesh, okay. Are you satisfied with the answer? Anyone want to like contribute? Any doubts now? A very important topic. MCQs can come from this as well, like the difference between shallow network or the deep network. Why we need, what is like, which one is computationally expensive, which one is having more neurons, which one is more efficient, and if shallow network is actually having enough neurons, so we don't need deep neural network if the problem is not that complex. But feature reusability and all other features are there. If the problem is complex, then it's better to switch to deep neural network. Any doubts? You got the concept? Please give thumbs up if you have understood, everyone. Only one thumbs up yet. What about others? Okay, let's go. So now ZMI. So basically, this is the ith input, and from Z, any M basically, ZMI. This is basically sigma. alpha. Can someone explain me what is this? Though I have told you, this is the function and this is like, can you tell me?
One is one is the function applied on the input, and the other one is the function applied on the hidden layer.
Yes, the function input and hidden layer. Okay.
COMM.
I'm talking about this one. What is this? This is sigmoid. Okay, this is the sigmoid function, the linear function. When we are applying on this layer, we are applying the linear function, non-linear function. Sorry, that is sigmoid function.
Okay.
So how we are writing is, this is the forward path. Like how I'm writing is alpha naught. This is basically simple line. Like we write the mx plus c the same way, alpha naught plus alpha m transpose xi. These are basically the xi, the ith input, any input basically. So wait a second, I'll write again.
So
So
I thought that second one was an alpha. Okay, that's a beta. Sorry, sorry.
yes. That is beta one. That sorry, that is beta weight. This is like we are doing now from so long, that beta naught m plus beta transpose mx.
MX plus C.
Uh,
MX plus
so
C.
it's like the same thing. Though the weights now, instead of beta, we are writing here alpha here. So this is basically when we are going from this is simple alpha naught m, any to m, any m basically. This is simple alpha naught m plus alpha m transpose x. That is how we write basically mx plus c. The same thing we have written. This is c here and this is mx.
And you're writing for bias.
This is bias.
Yeah, so
Integer bias.
basically this is a two-step process. First step is to, from the input, we
From the
multiply.
input, we are going to this hidden layer. So, what is this hidden layer? How we are getting this hidden layer? We are basically applying the sigmoid function. That is what we discussed. We are applying the sigmoid function, to which we are applying the sigmoid function. Whatever we'll get from here, what we'll get from here, this alpha naught m, I'll not write basically, maybe alpha plus alpha transpose x. This is just a matrix formation. Simple, we are applying this to the sigmoid function and then we are getting this z term. Getting this particular in ZMI. What is ZI? These are basically entire activity. Z1I, Z2I. These are basically Z1I till ZMI. I is basically ith input. Any doubt? Any doubt how I'm writing this? Again, I'll answer.
No, ma'am.
What about others? So what is this? This is basically the Z. How I'm getting this ZMI? How I'm getting it? Basically, I'm applying the whatever the output I'll get from here. What output I'll get from here? Alpha plus alpha transpose x. There I'm applying the sigmoid function. That's what we discussed. Like we'll have the sigmoid function or tan h function. So that is what my ZMI is. Now the other part is FKXI. FK, okay, I'll write here. This is basically whatever the output is there, that is basically the FK. So I'm denoting the output as FK.
In the hidden layer, we need to have two notations at one neuron. One before hello,
Yes, yes.
one before the application when the
One minute.
non-linearity is applied, and one after the non-linearity is applied. Because when
Yes. I'll come to
here,
where
we are able to see only one Z you are writing.
Z I'm writing. I'll come to the other part.
Okay.
I'm just writing the Z. I'll come to the other part as well. Don't worry. Now I'm writing the output layer. That is FK of Xi. I'm coming. Like how I'm getting this. Till here, I till here I'm talking. Till here. I'll come to this part. Fine na? This is non-linear as you said. Now this is linear or non-linear. It can be linear or non-linear. I'll come to this part. Is it fine or any doubt? Okay. Now how I get this output? Anyone? Now the weights are beta. Here the weights was alpha. Now similarly, this G, I'm applying, like here I was applying the sigmoid function because I was sure that I told you that we'll apply the sigmoid function, the nonlinear function. And as we discuss here, I can apply the linear as well as nonlinear function. So I'm denoting this function as GK. I'm not writing any sigmoid or I'll say tan h or anything, just denoting this function as GK, which can be linear, which can be non-linear as well. So here, now what is the output here? Can someone tell me how I have written? Sorry. Yes, can someone tell me how I have written?
Is GK the output from the previous?
GK is the function. Now
GK is
here,
then it's again MX plus C, but now you're using uh, the output of the hidden layer.
yes, yes. See, now I'm using here, it was like alpha x plus alpha naught. That was there, alpha transpose x plus alpha naught. Now here it should be beta transpose z plus beta naught. And then a function should be applied on it. Are you getting my point? Okay, I'll write here again clearly. So what is this? This is a forward pass. How I'm writing is, what should be z here? I'll write again. What should be z here? Alpha transpose x plus alpha and alpha naught, and here should be a function. Fine. Which I decided to take it as sigmoid. This was this z. Now I should come at fk. This output is basically fk. Fk, what is this output Fk? This I am denoting as Fk. What should it be? Similarly, now the input for this layer is basically Z. Like input for this was X. Similarly, I can write beta naught plus beta X, beta transpose X, and function, as I'm saying, is either it can be linear or it can be non-linear. So I'm denoting with G. Fine. Fk is equal to Gk, beta naught k plus beta k transpose Zi. Any doubt? Yes, Sachinji. Yes, Gaurav.
In that equation, you mentioned beta naught plus beta transpose x. So is it x or z?
Oh, sorry. X is the point.
Okay.
Because it's the input here is Z, not X.
And which function? So in earlier case, the sigmoid function has been applied. In this case, uh, it
It
is
can be linear, it can be non-linear as well. So I'm not specifying any function we can apply here according to the problem. Though I'll come
okay.
to
So g can be any function.
any function.
Okay. All right. All right.
All right. I am going in detail in mathematics because it's backpropagation and it's very important. So that's why. So now we are going to what is the loss function for the regression. As we have discussed, it's like sum of the squared error loss. That is what we are using. So yik minus fkxi, whatever the target is and whatever the output is, we got it, and sum of them, and subtracting it and squaring it, sum of the square error. Fine. Is this r theta fine? Come on. Can someone tell me?
Is R theta the final output? Then,
It's a loss function for the regression.
but then how can you have it? It can't be a loss function. You haven't differentiated it, right?
Okay, I will differentiate it. Loss function, what is loss function? How much, what is the target and what is actual out? What is what I am getting? Actually, FKXI I am getting. That's what we have seen. And what should be the target? In the regression case, we have done that. Whatever the difference between them, that is basically the loss. And now I am here using sum of the squared error loss. Sum of the
Okay.
squared error loss means sum and taking the square between the error. This is the error.
Square instead of taking a this thing instead
Yes.
of taking a modulus under yes, no
Yes.
understood, no understood.
Now, as you said that we'll differentiate it. So let's different. I'll again
Just
come to the
one
question.
question, I'm sorry, why two submissions?
Why two submissions? Okay. Can you tell? Okay. Can you check which are these
I
submissions? These are the inputs.
one is n to I to n, and then one
Hmm.
is I to k, but I don't
K,
know what n is.
K is equal to 1 to K. I are the inputs. These are all the inputs, and these are basically okay. This we were talking about one input only, one input function only. Now it will be for all output input function, and this is basically for the all output function. Maybe
So
I
k
should
is for
give
output.
some.
Okay, k is for output. Okay, got it.
Any other doubts?
No, ma'am.
So we are differentiating here. So I'll tell you, like, though what now we have done forward pass. Though I'll come again, I'll go back and I'll tell you the steps. What I have done, I have calculated Z, I have calculated the Y. Now what I am doing is I've said, okay, this is the loss function. I know what is Fk of xi. I have calculated that. Now coming to this, let's differentiate it with respect to beta, with respect to this weight. I'm taking here single weight, which means any output K, and this is any input M. So this single weight, beta Km, I'm differentiating it. Any doubt in this differentiation? So what I have done, okay. So yi minus Fk of xi square. First thing is like okay, someone told me to write the differentiation step formulas. Okay, sorry for that. Again, I forgot. Maybe you guys can do one thing, share the Google document with me if you want. Someone last time told me that if I can share the differentiation formulas of matrices and all at one place, you guys can do that, and I'll share with everyone so that others can also get the benefit of the matrices and all. Someone told me. So this is simple. Minus this 2 will come forward. Y minus Fk of xi. And what is Fk of xi? If we are ignoring the bias step, then that is like Gk of Gk, the function Bk transpose Zi. So I'm just Gk, what is its differentiation? Gk dash Bk transpose Zi. And now, what is the differentiation, the chain rule? What is the differentiation of Bk transpose Zi? That is basically Zmi. This step only someone told me, like if I'll differentiate with respect to x transpose C, the x I'll differentiate, then I'll get is basically the C here. So that's what here, Bk transpose Zi, if I'll differentiate with respect to beta, then I'll get the Z only. Any doubts in this differentiation step? Is it going above the head, or you guys are understanding what's going on?
No, ma'am, this one differentiation I understood.
So what we have done till now, just we have calculated this Fk forward pass. I'll again come. Don't worry if you guys are thinking what's happening. I'll again come to those things. And then I differentiated with respect to when I got this Fk, I differentiated with respect to this beta Km. Now, let's differentiate this the loss function with respect to the alpha Km, the other way. How we can differentiate with respect to alpha? We can't do it directly because R here, basically the loss function here, I'll say that it will depend on the Z, and the Z is basically depend on alpha. Basically, I can't take this loss function directly dependent on alpha. So I have to take a chain rule. So in which I'm differentiating with the Z, and Z is basically differentiating with the alpha here. So chain rule I'm taking. Any doubt in this chain rule? Why no one is responding? Is it that tough? Yes, Nay?
Would you please repeat the question, ma'am? I missed it.
I'm saying you got this step, this R
Yes,
with
ma'am,
respect to alpha.
yes, this is like a chain rule.
Chain
Yes.
rule, simple chain rule.
Yes, ma'am.
So now what is Z? We know that it's basically the sigmoid function to the whatever alpha naught m plus alpha m transpose x. That's what Z is. Now let's first solve this alpha Z with respect to alpha, and then I'll come to this step. So let's first solve this ZMI respect to alpha ml. Though I'm not explaining these indexes, I hope so you can see and you can look on these indexes how I'm writing it. I'm not going in that detail. So ZMI, let's take it as here also, let's take it as alpha m transpose. Let's ignore that bias thing. If I say that, okay, this is UMI, this whole alpha m transpose xi is UMI, how I'll write, if I'll differentiate, I can write sigma dash UMI, and I'll basically differentiate with UMI with the alpha ml. That's what I'll do. Or, okay, let's ignore this step. What I'll do here, I'll write simply rather than UMI. Let's write simply. So what is this? This is basically sigma dash alpha m transpose xi. Now with respect to alpha m, what is with respect to alpha, the differentiation of this? Come on, come on. If I differentiate with this with respect to alpha, what is the answer?
Ma'am, it'll only be M trans. Wait, it'll be XI.
Xi.
M
So
trans.
xi,
Yeah,
m
XI.
writing here. XIL, sorry, it's the index. So XIL. So that's what we have written here. That's what I got it. So this ZMI with respect to alpha ml, we have done. That is this term. This is the first equation. Now let's go to the second term. Ri with respect to ZMI. So again, Ri with respect to ZMI, we can't do it directly because Ri, that is the loss function. It is dependent on the output function. And then further output is dependent on the ZMI. Fine. And how I have written this this sum term, let's try to understand it. Till now, any doubt? And these are only differentiation steps, nothing else. What I'm doing is I'm just differentiating with respect to beta, the loss function, and now I'm differentiating with respect to alpha. As I can't simply differentiate with respect to alpha, the loss function, what I did, I differentiate with respect to z and then z further with the alpha. Now z also I was unable to do. That's why I differentiated with respect to, this is a chain rule. I'm differentiating with respect to f, that is the output, and output with respect to z. So why I'm writing this sigma steps, let's try to understand with a small example. Let's suppose I have one input, that is xi, one hidden layer, that is m, and output, one hidden layer, that is zmi, and two outputs, f1 and f2. So if I'll write f1 xi, what is this? Can someone explain me this f1 f2 xi so that I should know that you guys are getting it? Yes, Gaurav. Yes, Bimlesh. Yes, Yashwant. Sachin. Come on, let's try at least.
You want us to differentiate with XI.
No, no. What's this? What's this? I'm asking.
You've got two different models. Are you running this twice?
Actually, I have two outputs. No? There can be two outputs. What I'm saying is, it is F1 xi and F2 xi. I have one input, one hidden layer, that is ZMI, and two outputs. So for F1 xi, the two outputs are there. For F1 xi, I'll apply obviously in this. That's what I said. That here I'm applying the G function, the sigmoid function. G function, any random G function. So G1, it's nothing but beta transpose Zi and beta transpose Zi, the same thing. That's what I'm writing here. Getting it?
Are you saying two different inputs, two different outputs? Is that I'm still not clear.
One input. One input, that is Xi.
Output layer has two neurons.
Yes, yes. Output layer has 2 neurons.
And it is F1xi equal to G1 beta 10 plus beta 11 transpose ZMI.
ZM transpose actually, yes.
Okay, so what is the question?
So question is, let's like, are you getting this? What is F1, F2? Like what I have done, just I have applied a function on this is simply
F1 is the output on the first output layer neuron, F2
yes,
on the second output layer neuron. That's what you are saying.
yes, yes, yes. So that's what I was trying to mention here. 1 minute, 1 minute. So what I'm doing now here is like then I have to calculate this Ri. That is the loss function. Now what will be the loss function? What is the target? And what I got for F1 xi and what I got to F2 xi. The difference between them. And then basically that is basically nothing but the sum only. So how I'll get it? What I'll do it for this when I'll basically differentiate Ri with respect to F1, F1 with respect to ZMI, Ri with respect to F2, F2 with respect to ZMI. So I mean to say that's why I am using this sum, because I have whatever the outputs are for them, F1, F2, I'm using this sum here. This example was only given why I was using this sum here. This sum why I am using.
Got it, ma'am.
Got it? What about others? Is it too complex?
So this is the forward pass only.
Forward passing it. Oh, no, it will. Okay, I'll come to that forward pass and backward. I'll come to that. I'll not speak anything
No,
because
no, this when we are doing del Ri by del,
then it will
then
be
that is coming as a backward pass.
backward. I'll not speak anything because others will get confused if they haven't seen carefully. Okay. So this is basically now this fk is I know now I have to do this. That is, I mean to say here why I was using this sum term. So now I have this fk is equal to gk bk transpose zi, ignoring the bias term. Now let's differentiate it. If I'll differentiate it, any doubt in this differentiation? Can you see? This is simple. Uh, this yik minus fkxi square. So this will come forward. This is -2. And then, come on.
Then it will go inside an xi fkxi,
Hmm.
which is uh, fkxi is g to the power beta transpose zi. So first it'll be first the g function will be
Hmm.
differentiated, then it'll be
Beta k.
just beta. Yes.
Fine, because z with respect to z, it will be beta. Find this differentiation. Now, as we said that we are here doing, let's come to this. We were doing this Ri with respect to alpha ml. We solved this earlier. Now we solve this. Now let's put it together. So Ri with respect to alpha ml, we'll write this term. This is what I have written. The same term till here. And the other term. The other term, the first equation with respect to alpha ml. This one. So this is basically sigma dash alpha m transpose xil. That is sigma transpose. Fine. These are just putting equation 1 and 2 together. Fine. Yes, come on. Nothing, just I have put these 1 and 2 equations together. I have to put because I have done this differentiation, I have done this differentiation, and then put it together. That's what I have done here. Till now, everything clear? Now let's take minus 2 sigma yik minus fk xi gk dash till this term. Let's denote it as delta ki. Let's take it as delta ki to simplify it. Fine. What's delta ki? So this term is delta ki. Now what's left? This term. Let's take this delta mi as sigma dash alpha m transpose xi. This sum term beta km into delta ki. XIL is left still. Find these delta ki and delta mi. Come on. Only one thumbs up. What about others? Important step, please. Please give thumbs up if this is fine because I can't move forward. Nothing I have done, just denoted the terms. Yes, Gaurav?
Repeat again, ma'am. What
Okay.
just?
Till this point, you have got what I have written.
Yes, ma'am. You put both the equations together that we had separately done,
Now,
and then your minus 2
now
beta.
this term, what I'm saying is, let's take this term and denote it as delta ki. Fine.
Okay.
And now what is delta mi? Let's take this term, these all, and denote it as delta mi. This is
Okay.
delta ki, and including this term, let us take it as delta mi.
So we've just separated again.
Just not just denoted some terms. Though XIL is left.
Okay.
Just this is delta ki into this term, and this is delta mi. Like delta ki into beta k transpose sigma dash alpha. Just denoted something for simplify. Fine.
Okay. Yes, ma'am.
Now, let's see again. Now, if I say that, okay, let's first come to this differentiation of Ri with respect to alpha ml. Can I write it as delta mi multiplied by xil? This is delta mi. This whole term is delta mi into xil. Fine. Now, what is beta km? Let's just go again. If we'll see that this is the same term multiplied by zmi. This is the same term multiplied by zmi. This is delta mi multiplied by zmi. We have denoted already. This is delta ki multiplied by zmi. Fine. Till now, fine. Just I haven't done anything here. If you are confused, what I have done, I have taken the loss function, differentiated with the weights the way we used to do, differentiated with respect to alpha, differentiated with respect to beta, though we have used some chain rules here. And then I have denoted some, like this I have denoted by delta ki, and this multiplied by this is denoted by delta mi, and then just denoted with writing this delta ki and delta mi so that it should be simplified. Any doubts? Please give thumbs up if you have understood this. Come on, give thumbs up. Only one thumbs up yet. PKM is missing. What you're saying, Yashwant, I am not getting. Can you unmute yourself and explain me? Like,
There's a beta transpose k zi, then there's pkm. I think that's what he's asking from delta mi.
delta ml, okay. What he's asking, I'm not getting.
The second thing, delta ml has a p to the p underscore km.
Yes.
But delta mi already has pkm. Why would you write it again?
Delta mi already have beta km. It's beta km. Same as Gaurav said. Uh, Yashwant, is it fine now, or again you are having a doubt? This delta mi is already having this beta km. Okay, I'll just go for the go to have water. We'll have just 2 minutes break and I'll come back. Please revise these steps. Are these clear to you? Please revise it, what we have done. Then I'll give you how we have done it. Again, we'll discuss. This is a very important topic. I'll just come in 2 minutes, okay? Yes. Any doubts?
Ma'am, this is Sachin. There is no doubt as such, but from this derivation, what
Mhm.
can be the likely question in the
Okay.
examination? I
I,
mean,
I
the
come.
fundamental question in the examination.
I'm coming to the MCQs, okay? Don't worry. Fine now?
Okay, okay, okay.
Okay, I'll come again to the summary as well. You are getting Sachin what we are doing, the steps and all. Again, I'll discuss. Don't worry. So what
Yeah.
we have done, let's try to understand. This was the back propagation technique, like how we have done. Let's try to understand. First thing is, now I want, okay. First, you guys should tell me what is this forward pass. What I have written. Now I want you guys to tell me the step one. What I have written. We have solved the step. Can someone tell me?
You're putting an input.
Hmm. Okay, I'll hear again, right? This was the xi terms again. Sorry, these were x. This
Please
was
use some different colors. You're writing mostly black on black.
okay. Okay, is it fine now?
Yes.
So these were x terms. These were hidden layers. This is z here, and these were y here. So here the weights were like alpha, denoted by alpha. Here the weights were denoted by beta here. And here we were using the sigmoid function. Here we were using the function, which is basically denoted by the variable g. And here we were getting the x here. Now, you can tell me.
So in the forward pass, we are going passing through the network and calculating the basis the input and the weights and all the non-linearity functions.
Hmm.
We are going till the output layer.
Hmm.
At output layer, whatever we are predicting through the network and what is the actual yi, we are comparing that. Then we are finding the loss.
Hmm.
After finding the loss only, we are coming in the back propagation. Through back propagation,
Hmm.
we are calculating the gradients,
Hmm.
which is the actual learning phase in the entire network.
Hmm.
And through that learning, we are trying to minimize the loss in an iterative fashion.
Hmm. Hmm.
So
Exactly.
for forward pass is calculating the network output
Hmm.
at the output layer, comparing the prediction with the true level, and
Hmm.
then in the backward pass, doing all the gradient calculations and minimizing the error.
Hmm. Hmm.
That is how the
Exactly.
entire process is.
Exactly. Very accurately answered.
And at all the hidden layer neurons,
Hmm.
the calculation happens in two steps.
Hmm.
First step is, in the forward pass calculation of all the uh, stimulation and the bias,
Hmm.
summing them up. After
Hmm.
that summation, sending that through the non-linear function, and
Hmm.
then
Hmm.
after that, that becomes the output of that particular neuron, which becomes the input for the next layer neuron.
Yes. 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 Exactly. Exactly. So he has answered very correctly in detailed manner. So what we are trying to do here is, as we are doing a normal computation, first the forward pass. So these are just that equations only. What we are trying to do. So here, what we were trying to do is alpha into xi. That's what was the uh, and applying the sigmoid function. Then we'll get this hidden layer. That's what we were doing here. What is it? ZMI, particular ZMI, applying the function over the output which we'll get from here. So what is the output which we are getting? That is alpha transpose into xi, applying the sigmoid here. Now, what is the input for the y here? So what we are doing here is, that is applying the gk, applying any function that is g here, gk, k is here. So gk here to beta k transpose zi. The output which we are getting here is beta k transpose zi. So this is basically the forward pass. Any confusion in the forward pass? We came to this output. Any confusion here? No. Okay. So let's come forward. Then, as he said that, okay, we computed the loss function here. So loss is simply when we are doing the simple regression thing, then we are doing sum of the squared error loss, and for classification, we are doing the cross entropy. So here we were focusing on the regression step. So we use this, which is the target, and whatever the output function is, the squared of them, and the squared of the error term, and this summing up the all the outputs here. Now coming to the back propagation. Okay, done with the forward pass, done with the okay law. Then at output layer, we calculated what is this delta ki. We have seen that what is the delta ki, and at the hidden layer, we saw that what is delta mi. That we have done. Then what we are doing is, we are calculating the gradients here. Now, one more thing, it's the back step. Why we are saying each hidden unit's error is computed by taking the error from the output it is connected to. So now we are taking the gradient of them. So we have done that. Okay, we'll take the gradient with respect to beta. We'll take the gradient with respect to alpha. We have seen that these are basically the gradient which we got, that delta ki and delta mi terms, and then we are basically updating them in the iterative fashion. We have already done that, how to basically update them in the gradient step and the SGD. We have seen like how basically we are updating them. Any doubt now in the back propagation? Come on. So we have okay.
So, if a numerical question or otherwise MCQ is asked, then mostly the derivative of the function
Derivative.
output function will be mentioned.
Okay. Uh, maybe. Okay, because you can't solve. That's what I was also thinking. You can't solve the whole thing, and because it will be too tough in that limited time, na?
No, no. If it is not given, then it becomes a question, paper of
It will be.
calculus
Yes.
rather than deep learning.
But
Okay,
I think you should at least know, like, if something like a simple question like what is the
that
derivative?
is
Obviously, that it will not be there. But somehow, though I know the question like this cannot. But
that is why I had requested you earlier
uh,
to
one or
maybe
two
provide
questions.
us with common functions, the derivatives of common functions.
Okay, okay. You request. Okay. So, next time, that's what I'm saying. Please, if someone can do it and share it with me, it will be very helpful for me as well. Otherwise, I'll make the sheet. So, what he's asking, that we can have the common function of matrices and all the differentiation at one place, formulas, or like whatever you think. I'll suggest you whatever you think. Uh, some differentiation formulas you are getting, you are thinking about them, write in one place, forward it to me. In the next class, I'll forward that Google Doc. I'll also write from my side. So whosoever wants to contribute in that Google Doc, they can contribute and write the differentiation formulas if I am missing, if you are missing. Is it fine? We can work like this.
I have shared one cheat sheet for matrix and vector derivation differentiation
Okay, okay, okay. Where you have shared?
in the meeting chat only.
Yes, yes.
In the meeting chat only.
Okay, okay.
I usually use a differentiate. I take a screenshot of a differentiation question, put it in Chat GPT.
Okay.
Yeah, no,
Okay.
no, they get it. They get it right
We get
first
it,
year.
but in the exam, if it's like whole solve, oh, thank you so much. So he has shared it, the cheat sheet and all for matrix derivation. It's very helpful. I'll also add up here only, or I'll take this and add up in some Google Doc and all your sheet. Okay. So you guys, so thank you, Bimlesh, so much. It will be helpful for everyone here. So you can please download this and see. Okay, so as they are saying, okay, this is okay, this beta alpha. So we can also need this sigmoid and tan h function. So their derivatives I have written. Maybe I'll share it. I'll not telling now. Like I'll not solve it now. I'll share this. I didn't share the notes because there were other MCQs as well. So I thought that this week is not completed, and this PDF I'll share it once we'll complete this. So I'll share it after the class for sure. Don't worry. Okay. Maybe I'll not discuss this 26, 27. They are upwards only. You can see it. 28th question.
Ma'am, you may show 26 and 27.
Okay, okay, okay.
Yeah, yeah.
Can you try? I don't know whether these kind of questions will come or not. Just so that because obviously I want that it shouldn't be that like you are not able to solve it if this type of question comes there.
Okay.
I don't know whether they'll come, but maybe we never know. Yes, someone can solve it. 26 and 27.
I had once written down, like I once saw in a video how sigmoid is derived, the derivation is derived, and I
Hmm.
wrote it down. I can send a picture to you on an email.
Okay,
What?
no, no, it's here only. It's here only. I have written. That's what I'm saying. I have actually solved it. Maybe you can see it from here, like tan H. Maybe I have solved tan H. I don't remember. Last week only I have solved. So maybe you can solve it yourself, 26th and 27th, and you can see it. Okay. Is it fine,
Okay.
or you want to solve now? Okay.
Okay, ma'am. Oh, later, later, ma'am.
Later, no? Because it's like calculus only.
Yeah. Your
Ma'am,
screen is not
you're
visible.
not
One
you're
minute,
not
ma'am.
sharing it.
Okay, okay. 1 minute.
You are
Is it
based at
fine?
Tirupati IIT.
Yes.
You are at Tirupati IIT.
Yes, 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 yes. And currently I'm not there. I'm on maternity leave actually. Gaurav, it's not weak. Maybe you can. I give you time because it will take a lot of time here, and I have solved it above only. I'll share this document. So 28th.
Okay.
Error signal means error.
Error only. Error only.
It means loss, is it?
Yes, 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 yes.
Okay. So it was square error, right?
It was squared error.
And so here the differentiation of square error, right?
Is yes, yes.
So
So it'll
C,
always
is it
be C,
C?
right?
Huh,
C.
yes, yes.
No, no.
Please
Why
write
it
the
will be
answer.
C?
So it is like sometimes it will be like you don't have to solve it. It will be obvious from the options like this. You
No, no.
don't
The
have to solve
question is
it.
asking for error or the differentiation of error.
Actually, it should be error differentiation. Maybe it's my. I shouldn't write this. Gradient basically.
This is the question. Answer should be A.
No.
But okay, if it's not a loss function, we are saying maybe it should be gradient. Something. Okay, it should be gradient. Then it's C. What about 29? The hidden units delta mi is computed by direct difference between target and prediction weighted sum of output deltas time hidden derivative squared error at hidden layer sum of input to the hidden layer. Please write it in the chat.
Weighted sum of output.
Weighted sum of. Please write in the chat so that others can also get the time to think about it. It's like weighted sum of output deltas time hidden derivative. How? Is it
Ma'am,
tough?
we took the squares, right? To
Okay.
check. I
Okay.
thought we took hidden unit square.
Wait. I'll come. Now what they're asking about? Delta mi. Let's see. So this is delta mi. What is it? Delta ki multiplied by this term. So what's it? Weighted sum of output delta. Okay, output delta. That is what? Weighted sum. Weighted sum of output delta time hidden derivative.
Okay. Okay.
Fine.
Yes, ma'am.
Fine. Na?
Yes. Yes.
Which of the following best explains why backpropagation is efficient? It avoids computing the loss function. It computes gradients by propagating error signal layer by layer. It directly inverts weight matrices. It replaces optimization with random guesses. Please write in the chat. Here, okay. This time everyone has written before. Everyone should participate. Everyone should write. All 12, 13 candidates who are present here, please write. Dr. Pepuri, please write the question as well. Like 30, 31 years. Yes, everyone is correct. So, which explains it computes the gradient by propagating error signal layer by layer. For ReLU activation, okay. We haven't talked about ReLU. Some other day, I'll come again 31. I'll come again to 31 afterwards. The update, the weight update rule for output layer is yes, absolutely correct. It's B. The gradient with respect to hidden layer weight alpha ml is Now only we have solved.
Ma'am, could you please quickly explain what is gradient? I mean the concept.
Gradient is nothing, the differentiation thing, what we have done. That is what I'm talking about.
Differentiation
With respect to alpha, we have done na here.
loss function for loss function, right?
Loss function. That is what that this is delta mi into xil. That's what I was asking. Fine, na?
Why they call it gradient actually?
Can someone answer his question? Why we are calling it as gradient? Come on.
So it is multivariate and we are calculating partial derivative.
Hmm.
So it basically gives the lowest steepest accent on a smooth curved surface, and so that is why it is called the gradient of the curved surface, and that is the steepest, the line of steepest ascent.
What is the difference between gradient and differentiation? Have you thought?
I wouldn't say. Actually, its gradient is a
It's a
par visual representation of a differentiations only, ma'am. What you're expecting is that when you're saying taking a gradient, you're expecting that the bottom of the gradient is where the minimum loss would occur, which is like the most accurate value. And
That is, you both have answered correctly. That we are finding the minimum slope, that is like gradient descent, or that we have done na the and all. What is the
we call it gradient because it is the collection of partial derivatives, and that
partial derivative?
yeah,
Can I
the
say?
entire collection is called the gradient for that smooth surface.
So can I say that if I talk about like a very if I talk about differentiation, it's like yeah, I'm taking a single variable case. And if I'm talking about gradient, I'm saying that I'm taking multivariable case. Multivariable case means the function depends on many variables. The gradient is the vector of all partial derivatives, I'll say. Like delta f, I'm saying it's delta f, delta x, delta f with respect to delta y, and delta f with respect to delta l. So basically, it depends on many variables. For that case, it's gradient when we are doing this partial derivative. And if it is dependent on one variable, can I say it's differentiation single variable case? Have you ever thought of this? Yes. Am I correct, or you're getting confused? Have you ever thought in this direction? Like in neural network, if I say, then like delta j is like uh, partial derivative with respect to W1 with respect to W2. Yes, come on. Have you ever thought in this direction that why are we interchangeably using differentiation? He correctly answered that okay, it's partial derivative. Can I say it's multivariable and it's a single variable case? Yes, Bimlesh?
Yes, it is multivariable case.
Yes. Yes, Sachin, have I answered your question?
Yeah. I mean, I was trying to understand the
Basically,
intuition. So gradient in real
differentiating one at a time
Hmm.
for all the variables,
Hmm.
and and then deciding which is the best direction for ascent for
Hmm.
descent.
Hmm.
So it means in real life,
Hmm.
because in real life problems will involve multiple variables, and in that case, the gradient will be used. I mean, the partial differentiation or partial derivative will be used.
Hmm. Hmm.
Uh,
I
uh,
can in simple language say gradient is just differentiation in higher dimensions.
yeah.
So 34
Partial derivation. I mean,
partial derivation.
higher degree means it is again second order, third. So it's not that. It is basically partial derivation.
Yes, yes, yes.
Yeah.
No, no, no. Degree is something is degrees of the function. How many variables are in the function? That is another thing.
Yeah, yeah, yeah. Yeah, I understand.
Understood now. I don't have to write now. So
No,
that
no, no.
uh,
I mean,
20 F.
intuition is clear. Yeah.
Yes, yes, yes. Okay. 34th question. Why do we introduce delta in back propagation? It's simple, very naive answer to reduce storage costs too compactly. So sometimes the questions can be very simple to compactly represent repeated chain rule terms to eliminate the need for learning rate to avoid far forward fast competition. And you can think, okay, you shouldn't be that time thinking, okay, why it's so simple? Is it like that or is it I am getting confused?
Too compactly.
A very simple question. Naive answer. Why we use delta? I told you earlier also. Yes, exactly. What about others? I'm waiting for others to answer.
Um, just 35 is also the same as the first two, right? It's differentiation.
Yes, 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 yes.
Okay.
I'm not doing differentiation. I'm leaving up to you. And I'm writing the answers also. And if you get some difficulty, you can mail me or in the next class we'll solve it. Because it's calculus only, I'll not do. Come on. Only two people have answered. Very simple. Yes, exactly. So, sorry, it's B. So what I'm saying is just I'm using delta so that for simplicity, nothing else, to compactly represent the repeated chain rule terms. In softmax with cross entropy loss, the derivative simplifies to maybe you can see, though it's simple only. Which activation is most likely to suffer? Okay, vanishing gradient we haven't done. I was okay. Back propagation is an essentially the application of exactly the chain rule. Suppose a hidden unit output is this. Its derivative with respect derivative I'm not doing. 39. In back propagation, error flow from input to output, from output to input randomly across layers only in hidden units. Okay. Why you have answered B or why you have answered A? Someone? The answer is B. Okay. Whosoever has answered B, can you explain? Because someone has answered A as well. Why error
Uh,
flow?
Forward pass, once we get what is the error, we go back and we
Yes.
then we added like going back with the learning rate.
Yes, yes, exactly. First, we are going to the forward path, but when the error, if we are
Error
talking
is
about the error,
always calculated at output layer after the completion of forward pass and the prediction. Now,
yes,
after the prediction, the error will flow back to the input layer
yes,
so
yes,
that all the weights in the network can be adjusted, so
hmm,
which will help in minimizing the loss in next iteration. So
yes,
that is why error will flow from output to input.
exactly, exactly. 40th, which one is true about the weight updates in backpropagation? Every update is delta into input, every update is error into input, every update is delta into output. Updates don't depend on inputs. This is also simple one. Gaurav, can you again check?
Okay, it's output for sure. It should be error, right? I'm thinking delta because of the sun, right?
Bimlesh also, can you check? Think again. Is it error? Is it input? Why it's output?
If you wouldn't mind, would you scroll up? Can I see, is it xi or ki?
Uh, Okay, one output. Now we are saying each one is true about weight updates, and every update is Bimlesh, Gaurav, please check.
Input. Input.
Yes, Bimlesh?
No, I was thinking of calculation in the backpropagation. So every step is coming from the
That is something else, right?
layer L to layer L minus 1. That is what I was the update. Okay, so basically here after the entire back propagation, when we come back to input layer, after that weight update happens.
So when I'm talking about this gradient thing, that is when you see that, that is basically delta into input only, na?
Correct.
Average also. Okay. So let's move forward.
I was thinking that out of 10, 8 is B.
I was
So
thinking that error thing. That's why
I
maybe the error is going from out.
was thinking like out of 10 questions, 8 questions are answer B. So blindly putting B here will also get.
Rather about this. These are my questions. That will not be mine. Okay. One. Just. Everyone is getting because only 2 or 3 people were answering the class. So everyone has got this ANN concept, like clearly how this backpropagation concept.
Ma'am, can you quickly give intuition behind delta? Now we have studied this back propagation and we are referring to delta. Uh, so can you please clarify what role this delta plays?
Can you read this 34th question? Why do we introduce delta in backpropagation? Just for the simplicity, nothing else. When
Okay.
when I wrote the whole equation, I wrote this whole equation. It was very like looking like very complex one. So what I said to compactly represent it, I mentioned this is delta ki and this is delta mi. Nothing else. Got it? Don't confuse with this so that I can like I want to briefly like what is alpha ml so that I can like represent this delta mi rather than writing a whole equation. I can write it simply by writing this delta, nothing else. Fine, Sachin?
Yeah. So it is basically substitution for.
Substitution, right term.
Okay. Okay. Mhm.
Hmm.
Yeah. All right. Thanks.
Hmm. Any doubt? So in gradient descent, we have done that where to start and all. There is always a question with us like, do we what do you think? Like we should start from the same value. We shouldn't. We should start with the random value. Like from where to start in this gradient descent? Can you quickly tell me what is gradient descent and what I am saying starting point and all? Come on, come on. What I'm referring to starting point and all, can you quickly tell me?
You're talking about putting the weights, the connection between that, the weights you put alpha and z. You should not put them all the same. You should. I think you're saying you want to randomize them.
Yes. So, what I'm saying that in gradient descent, what should be the starting point? Starting point means like whenever I start this, let me first come to the equation. So in this equation, what I'm referring to the starting point? Can someone tell me what is the starting point here? Come on.
Weight multiply by input.
Wait, the first one, can I say? The old one? This
Yes.
one, old one. That is what the starting point is. So what I'm saying is, like, let's have the starting point, the old update minus what we usually do when I write the gradient descent. The new update is equal to old update minus the step function into the gradient term. This is the formula. This old update, I have to take something in the first place. If I'm updating alpha, if I'm updating beta, when I'm doing the first time I'm updating, I should have something, na, the starting point. Okay, I can do, like, this is iterative method, as you guys only told me, ma'am, it's an iterative method. But like, suppose, sorry, again, I'll use some random color. Okay, beta new is equal to beta old minus step function into the gradient thing. I'll just write a differentiation. So this, or sorry, gradient of the loss function or whatever we are using. So this beta old for the first time. Okay, this beta old for the second iteration, what it will be? Can you tell me? For the second,
Beta
beta.
new from the first equation.
Exactly. But what will be the beta old for the first one?
Some initial conditions.
Some initial condition. That's what I am asking. Now, what should be that starting value? What is the, what if I take all zeros? I have written here, you can see it's not a good choice. Why? Why not to take everyone same? Have you thought? Come on. You got the question. What I am asking? Starting value, this beta old. Okay, for the second iteration, as he told, the beta old will be the beta new of the first iteration. But what will be the beta old for the first one? Because I have to start from any point, because now I don't know what is beta. Can I take it all same? There are many questions which come to our mind. So what is the symmetry problem? Can you tell me? Any idea? Any idea? So suppose I have the same input. Okay. And suppose the weights all are 0 or all the weights are identical. Then the output will be identical, I'll say. There'll be no benefit of having the multiple neurons. Are you getting it, or I should explain in detail? Can someone tell me what is the symmetry problem again? Yes, who have unmuted? Yes, Gaurav?
Um, uh, for example, if you give equal weightage to each and every neuron, all of them will be activated. All of them will start contributing to the answer, but you don't want that. You want only certain to be activated and contribute at certain situations
Yes,
based
yes.
on the input.
Yes. So what I'm saying is, suppose we have, uh, as he has also told, both of them, they are receiving the same weights and same. Yes. Yes, someone was speaking. I don't want that two neurons should give me perfect clones. They should be like equal. Because I want that this two neurons, they should have their they should they should give me an not unidentical output. Basically, they shouldn't be identical forever. So that's why I don't want if I'm having the two same inputs also, if I'm having the same input for them, both of them, the two hidden neurons, like, okay, sorry, same input for two hidden neurons, I don't want that they should give me same output, because if W1 here and W2 here are the same, will I get the same input, or will I get the same output?
Yes.
The same. Yes, that's what. Then what is the benefit of having multiple neurons? There is no benefit of having multiple neurons. It's like it's equal only. So no benefit is for me is there. So that's why I want that W1 and W2. It shouldn't be same. It shouldn't be identical. So or it shouldn't be all zeros. So that's why I went to random initialization. And the other part is I want the weights to be small. Why I want the weights to be small? Any idea? One thing is we studied about the symmetry problem. Okay, the starting point shouldn't be the same, and because there will be a symmetry problem there, that's why we switched to random initialization. Now the other thing is we want that all the weights should be starting from small weights, but all shouldn't be zero. They should be random only. So I want small random weights not to be zero. Can you tell me? Okay, maybe has professor discussed about vanishing gradient problem? I don't think so. No? Have we discussed about this? Yes, come on, come on, come on. Can you tell me?
Yes, basically multiplying very minuscule numbers several times
Hmm.
will ultimately lead to gradient coming out very minuscule. It
Hmm.
will be
Hmm.
kind of like all the gradients being computed are almost the same or flat.
Hmm. 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 I want to maybe I want all of you to at least study in detail about, as he has given some gist of it. I want everyone to study this vanishing gradient problem, though professor haven't discussed. I want you guys to see about this. Now, what I was talking, if the weights are too large, can I say there will be exploding activations, which means like Z is equal to WX, it will be becoming that thing. I want that it should be near to zero, but not zero, and it should be smaller in weight. Oh, sorry, and it should be random here. So small changes in the weights having the what is sigmoid here? Can I say this is sigmoid function? Anyone, can you tell me about sigmoid now? We have already discussed left and right about sigmoid. Maybe this one is vanishing gradient and other I'll tell you exploding gradient problem. I want in next class you should answer me before starting the next lecture. What is vanishing gradient? What is exploding gradient problem? Exploding gradient, it is related to that it will become large. It because as you'll go backward layer by layer, as we are going in back propagation, it will become large and large, and it will grow exponentially. So that's why we are having the small waves. Now, can you tell me why we are using sigmoid here? You know the answer.
It can be differentiated, right?
That is there, but why here? Okay, that is one thing that it can be differentiated. It's a non-linear function. It can be differentiated. Okay, Gaurav. Okay, okay. I'll upload the class on YouTube. Yes. Can I, first thing is obviously it's differentiable. And can I say it's like 0 to 1 only? So it's easier for me. Can I say that?
Yes.
Yes. And the other thing, as he told that it's differentiable, the max it's like 0.5 and the max derivative will be 0.25. The other thing in the neural network is overfitting. Okay. This we discussed that we'll use sigmoid, we'll use randomized. These are some points which can come in MCQ. Why not to use zeros, quarter symmetry problem, something like that. Why not to use them? Is it we should use randomly or we should use the same values? And the other thing is, what is overfitting? You know overfitting? I have given you many layman example. Anyone can answer what is overfitting? There are many overfitting cases which we can see in neural networks. Why? And what we can do for to avoid overfitting? We have already done something. Can you tell me first what is overfitting? Come on.
So large number of variables are being considered.
Large number of features are being considered. Like I gave you an example. If in training, if I in like I'm telling you that this is a, I gave you a very simple naive example. If I'm telling you a ball, I shouldn't basically try to cover each and every feature. So that's basically overfitting. So if I'm telling you this is a ball, and suppose this ball is of red color, so whatever what I'm saying, okay, this is spherical in nature. The feature I'm trying to say, okay, this is used to play. Okay, if suppose I'm giving the radius is supposed 2 centimeter, and it's red in color. Obviously, we don't need these much of features. If I'll give these much of features and in testing I'll get an orange ball, what I'll say, is it a ball or no? What will be the answer? Yes.
No, it will not give answer as ball because we have defined color as red.
Yes. So that's basically an overfitting. We are trying to cover each and every feature. So what we can basically giving large number of parameters and making it complex. So what can be the solution? One solution we have already done, that is regularization. L1, L2 regularization we have done. We have discussed in detail about lasso regression and ridge regression. L1 basically promotes sparsity. We have done how it promotes sparsity. Remember what is which one is L1 is L1 norm, one is ridge or L2 norm? Which one is lasso? Which one is ridge regression? Come on, fast. Come on. Come on. Forgot. L2 is ridge regression, L1 is lasso regression. And L1, maybe you can see. I'll suggest everyone now look, watch the lecture, watch the previous lectures about how it is promoting sparsity, lasso regression, and L1 is lasso regression. So, I have discussed in much detail about this, and I was hoping that you should answer it correctly. Okay, first case regularization we have already done in our previous classes. Second, tie parameters. Can someone tell me what is tie parameters? So what I'm trying to say here is, okay, when we have overfitting, one way is regularization. Second is we can force some weights basically to share the same value. Some weights, now I'm not saying all are having the same value, but some weights can have same value so that we can be free from some parameters. That's what our main motive is. Or I can find how I can be free. How can I have that? One way is like one other way. Okay, one is that tie some parameters have the same weights for some like value. The other we can think of is remove some parameters. How remove some parameters? Some suppose I am saying that some weights are having low sensitivity. Okay, English one. Hmm. what I'm saying is some weights are having low sensitivity. So if we are having low sensitivity, remove those parameters. Can you tell me what is this remove parameters, weight, low sensitivity? What is this low sensitivity? What I'm referring here is, come on. Come on, come on. Okay. One was regularization. One was okay. Have this is simple one, naive one. Have the same weights, though it's not a like optimal approach. Like I'm having same weights for same weight value for some, so that some fewer parameters could be released. The other, I'm saying find the weights with the low sensitivity and remove it. What do I mean by that? Come on. Come on, come on. What do you mean by low sensitivity? Yes, Bimlesh. Sachin. Satyarani, yes. At least try.
I think low sensitivity means uh, if um, we vary the weight, then we may not see much difference in the output.
Exactly, exactly. So that's what I'm saying. Like, okay, this algorithm is basically, there is a detailed algorithm, though only overview was given. That is basically optimal brain damage, which says that find uh, find low sensitive weights which are not having much uh, much contribution. Many weights, they are unnecessary, which are causing overfitting. So let's remove that unimportant weights and make the model simpler. That's what is optimal brain damage algorithm says. Brain means network, damage means pruning connections, pruning means removing connections, optimal means trying to find the optimal parameters. Optimal means trying to find those parameters. If I'll remove them also, I'll not have much difference in my model, or it will basically reduce the overfitting. That's now the other is validation. How this validation data set, validation will help me. I have drawn some figure. First one, we have seen some methods, regularization, time parameters, optimal brain damage. How this validation will help me? Can someone tell me? Come on, come on. Let's try. Try at least. Look at this figure. What I'm trying to say is, okay, I did some training. In my training, and I did some testing. When I did the training, the error was decreasing. And when I did the testing, at some point, the error is increasing. That's what happens in overfitting. We have already discussed in detail, like this is the figure. Any doubt in this figure? Is this overfitting figure? Any doubt here?
No, no doubt.
Can you elaborate, ma'am, please?
Yes, yes. Okay. So what I'm trying to say here is, when we do overfitting, when there is an overfitting when it is, so overfitting, I'm trying to fit every feature. As I told you, suppose this is a ball. I'm trying to fit, okay, it is spherical in nature. We are able to play with this object. So, and suppose I'm trying to fit an unnecessary features, like suppose it was a red color ball. So I tried to fit, I said, okay, whichever object is red color, whichever object is spherical, whichever object is used to play, whichever object is having the radius this much, that is a ball. And when an orange ball was given to me, I said, no, it's not a ball, because I have learned each and every feature which was unnecessary to me. That is like a red color object is always a ball, which shouldn't be the case. So in training set, as I was trying to learn each and every feature, my error was 0, like reaching negligible. When I did testing, at some point, my error basically increased because it was trying to cover each and every feature. And suppose an orange ball came, so my error basically got increased. So that's what happens in overfitting case. The testing error is increased, whereas training is not increased. That is overfitting case. Now, what does this mean? A validation or empirical steps, what I have to do is, suppose I know that I have to remove, though I have to remove this overfitting. Now, what I'll do, whenever adding the parameters, like I added spherical in nature, then my testing and training both were giving the good results. Then I added somewhat okay results. The error was decreasing. Then I added okay, the object we can need to, which we need to play. Like then the error was decreasing. Then I added the object which is red in color. Then we saw that when adding the parameters, the testing error with the iterations, it got increased. We have to stop. We have to find, like, in which adding parameters the error is basically increasing. The testing error is basically increasing, though training is decreased by adding few parameters when it is increasing. So I have to stop there. That is what I'll come up with the validation. Any doubt? Any doubt? Any doubt in overfitting and how to reduce the overfitting? You have, this was just an empirical, no experimental or empirical, I'll say. No need to like worry about this. The first one technique to reduce is regularization, tie parameters. Then we saw this. This is actually related to this low sensitivity weights only. Like I tried to find that this weight is basically low, not that much sensitive, not that much contributing. It is contributing to overfitting. So that's why I removed that parameter. Now the other, okay, please give me thumbs up if you have understood this concept. What about others? Okay. So why we usually, the important part is why when we are given the inputs, the data set, like when we are given the inputs in machine learning, why we usually scale it. So basically, the scaling of the input is necessary. The other part is because one variable, suppose it's very large range, another is very small. And when we are going to do uh, it will, when we'll do the gradient computation, then it will dominate over other just by being numerically large. So I don't want that. So that's why the scaling is basically necessary.
It is also called as normalization, right?
Normalization, yes, yes,
Yeah,
yes.
yeah.
Coming about local optima. What about SVM? When we talk about SVM, we always talk that we have, what is the difference that we always talk between when we talk about perceptron learning, SVM, and all of these. We always talk that SVM has an advantage that it always, the goal of SVM is to find an optimal hyperplane. Basically, only one global optimum exists, no local minima exists, which means I'm finding the optimal one that we have discussed in previous lecture in SVM. But if I talk about neural network, it's fairly complex. If I talk about the error surface, it's very complicated. Like it's having, when I'm doing this, it's having uh, like so many local optima. Local optima means here, suppose I am stuck here. I'll think, okay, this is my minimum step. Okay, GD, what I have to find out the minimum slope. So I'll think, okay, I'm stuck here. I'm moving left and right. I'll think this one is there. So that is the limitation which we can find out, that error surface in ANN is basically non-convex. In SVM, it's basically convex. Can you tell me the difference between convex and non-convex? Come on. Can you tell me the difference between convex and non-convex function? We have discussed about optimization and all. Convex optimization. What is the difference between convex function and non-convex function? I am saying that AN basically it's non-convex, whereas SVM is convex.
In a convex function, if you draw a straight line, cutting the curve of the function, it cuts in
Inside.
at most 2 points.
Yes. So, okay. What about this? Can I say, okay, one more, in context of this, can I say in convex function, the property of this, okay, I'll not go in much detail about convex function. I'll just say the main property where what I'm referring here is, like here, I have single global minimum point in convex function. In non-convex, there are local traps and it is like we have multiple local minima and maxima. So, like this. So I can be trapped here. I can think that this is my local minima.
Yes. So in non-convex, I mean, the initialization will affect where you land up in a local optima or a global optima.
Exactly. So I can be trapped here. What can be the solution so that I shouldn't be trapped? Okay, we have done here in ANN some limitations and we tried to do that. Okay, how we can overcome it. First was the part initialization, how we should initialize. We said, okay, initialization should be random. It should be close to zero. Not everyone should be zero. Otherwise, we'll have a symmetry problem. The other thing we discussed about was the overfitting problem. Then we discussed about regularization, tying the parameters, optimal brain damage. And then we discussed like we should also scale the inputs. The other part we are discussing that we can be trapped in the local optima. Now we are discussing how we'll basically come up with the solution. So here a very naive solution is there. Like either like suppose I'm starting with the random weights, I'm training until I'll converge. If I'm stuck in the bad solution, I'll again start with the random weights, but I have to remember the previous weights. Why I have to remember the previous weights? What do I mean by I'm starting with the solution, repeat it? Can someone explain these steps, what I have told you? Come on. Come on. Yes.
What is convergence? I mean,
Convergence means I have come to the result. Like now, stop it. Now it's fine. Like it's my minimum point. I am not okay. Convergence means when I am doing the iteration now, like new update, old update, that is basically not changing. If it's not changing, I am thinking, okay, this is my final result. It has converged. Fine. When I'm doing this beta new is equal to beta old minus uh, this this maybe I'll write this. So when I'm doing this, so what I'm saying is I'm doing multiple iterations, and when they are not changing, I am thinking, okay, this is only my final beta. Now it has converged. I have find the final result. They are not changing with the suppose I did 11th iteration, then 12th, then 13, all are having the same beta result. So it's like my final result. But it's actually not the final because it has basically stuck here somewhere. It's not going to the because I'm starting with some random weights. So what should I do? I'll start with some random weights. I'll train with some convergence. If I'm stuck somewhere, I'll again start with some random weights. But I'll remember at first one, like when I did it for the first time, what were the initialized weights? So that suppose like what were the resultant weights? So that maybe the first time which I have tried, that was the best one. Second time I tried, third time I tried, fourth time I tried, and I find out the first one was the best one. So I have to remember it. Fine? Any doubt?
Yes, it's fine. Yeah.
Please give me thumbs up. Yes.
Yeah. Only question is how many times uh, we have to keep on restarting.
Yes, sir. That is
So
the
there can be many non-convex surfaces. And
it's again like that's another line of research, like, or like how many times we should do, like it's like another line of research. Sometimes some like either it's like empirical only, it depends on you, it depends on the computation, how much you can do. There is no answer for this.
okay,
It's
is there anything called as keeping it in memory? Um, uh, suppose we did a few restart and then we are observing that we are continuously getting same result. So
then it's like the same. You can take any weight. Okay, though we usually do 30 times. Okay, I'll not. I'll come to this someday. Like how 30? Why I'm using this 30 number? I usually when I run the experiments. Okay, I'll come to this afterwards at the end.
yeah, no problem. We will discuss later. Yeah. It's already a little late.
No. Like I don't want to tell you about this because it will be confusing. It's something related to some formulations and all. Maybe some other day. But this is. Experimental only, like how many times you have to do. I'll come to this number. I'll come to your question some other day. Okay. Overfit. Okay, let's do this MCQ and end the class. Overfitting in ANN means central limit. Yes, Vimlesh. This is central limit theorem. I'll come to that. Exactly. Overfitting in ANN means, let's quickly solve it. Only two are answering. I want everyone. Many of you have left the session also. 10, 11 students, whosoever are present, 10, 11 candidates, please answer it. Trishi, I want the, please, I request you write the question as well. Yes, exactly. Model performs well on training, but poorly on testing data set. Which of the following does not reduce overfitting, dropout, L2 weight decay, increasing number of hidden units, early stopping? Exactly. Though, like, you can answer it. Maybe we haven't discussed some terms also, like, but you can answer it. Obviously, this is like if you'll increase the hidden units, the overfitting obviously will not be reduced. Parameter tying reduces overfitting because it increases training data size, it reduces the number of free parameters, it prevents gradient descent, it eliminates non-linearity. Come on, guys. Come on. Yes, it's actually B. It reduces the number of free parameters. Optimal brain damage is initializing all weights at 0, random restart for escaping local minimum, structured pruning of unimportant weights using second order approximation, increasing hidden layers until validation error. 44. 43, okay, Bimlesh. It reduces the number of free parameters. What we have done, like same type of weights, like same parameters, we are giving to many inputs. So that's why I'm saying that we are reducing some parameters by, okay, I'll explain this 44th. Optimal brain damage is what I'll not, okay, I'll not describe this. Maybe this will not come because it's like using second order, maybe ignore this. But obviously it's like structured pruning of unimportant weights. Pruning means removing. So what is optimal brain damage? Optimal brain damage is whatever the unimportant weights are there, which I told you, which are non-sensitive, as I have mentioned you, and I asked you what are non-sensitive. You told me, one of you told me that they are unimportant weights. So I am basically removing. Pruning means removing those unimportant. There is some way to remove those unimportant weights, which are basically yes. Validation set is used for updating weights directly, tuning hyperparameters, and detecting overfitting, reporting final performance, replacing training data. Exactly, as we have done that, it is basically detecting overfitting as well as tuning hyperparameters. So, which statement about validation and testing is correct? Validation set is used to tune model. Testing is for final evaluation. Both validation and test are used for weight updates. Test set is used for hyperparameter tuning. Validation set is never needed if test set is available. Exactly. This is basically A. So we are basically tuning model, and for validate, it's like for final evaluation. Validation can be used to choose number of hidden layer, learning rate, dropout probability, all of the above.
All of
Yes. Validation basically it can be validation set. I can see like how many hidden. Maybe I skipped that part, which I shouldn't by mistake. So validation, okay. Here I have written also like try one layer, what best you can do, and add another layer, and we can check it empirically by adding a layer. Will it be useful or will it not be useful? So that is basically validation set is helping us. Scaling inputs before training in ANN because it reduces training time and avoids saturation. It removes the need for the bias term. It guarantees convex error surface. It prevents overfitting completely. Scaling inputs basically it reduces training time and avoids saturation in activations. Why? Why?
Yeah, basically different inputs having different magnitudes. So it may lead to some erroneous assumptions about the inputs by
Because
the
it's
network. So
numerically large. Yes.
scaling them and normalizing them
Hmm.
makes all the inputs almost in the same scale. So that magnitude influencing the weights, I mean, it is taken care of.
Yes.
And then the entire training time is reduced because that part is taken care of.
Yes. Exactly. Correct. In neural network, there are surfaces usually. Come on. It means there are surfaces. Fun. I don't think so that I have to explain it. I hope so that you guys know that why I'm saying there's convex and why I'm saying non-convex. Random restart in ANN training are used because they guarantee faster convergence always. They allow escaping poor local minimize saddle point. They avoid the need for backpropagation. They replace gradient descent. Exactly. Momentum and gradient descent help mainly by can I say reduce oscillations and accelerating the convergence? Exactly. The reason we initialize ANN weight with the small random values near zero is Maybe I haven't discussed. I hope so. You're getting it. Which of
Hmm.
the yes, yes. Maybe I'll discuss in the next sensitive region, not sensitive. Okay, I'll discuss. Which of the following is not a technique to reduce overfitting in ANN? Yes, come on. Weight decay is regularization. That is a technique. We have done that. This is weight decay. Adding the weight decay regularization session. So basically, again, increasing hidden layers will not reduce the overfitting. Fine. Most of this backpropagation ANN part is covered only. So next, I'll say that please, because we don't have much time, I'll request you go through those video lectures about decision tree and evaluation measures and all. We'll next time I'll briefly introduce and I'll come with the MCQs. No, I'll not go that fast like I'm going here with the MCQs, because here I'm going that fast because I know that you guys I have already discussed. There I'll go slow and explain each and every like part of the MCQ. Is it fine? Okay, thank you, class. We'll meet in the next class, and Saturday I'll take an extra class. Maybe you'll
Thank you
get
so
the
much,
link.
ma'am. Happy Dasra, ma'am.
Yes. Yes. Any doubt? Okay. Thank you, class.